Exercise 20. So we discussed the exercise in the previous video also. We are given a non-empty set S and a partition on S. Using this, we have to define some equivalence relation on S whose equivalence classes are precisely the sets in the partition. So let's see how that can be done. So the set is already given to us. We will now have to consider a partition. Let P be a partition on S. So that means what? Let's just first see what that means. It means that P consists of some subsets of S which satisfy these conditions. Each subset of S in that is an element of P is non-empty. As a subset of S that is non-empty. And if we take two distinct sets in P, that is two distinct elements in P, then they must be disjoint. And the other thing is that if we take the union of all the elements of P, then we get the entire set S. That's what being a partition of S means. Okay, so now we need to define an equivalence relation. Let's just define it like this. We now define a relation tilt on S as follows. For two elements A and B in S, we define A to be related to B if there exists some set in the partition such that A and B both belong to that set A. Okay, now the next job is to show that this is an equivalence relation on S. So first, reflexivity. So let A be any element in S. In fact, let's just write that. Let this be any element. Okay. Now because the sets in the partition unite to give us the entire set S, that is, since S is equal to the union of all the sets, we can call the general set in P also A. Because of this, the element A in S will belong to at least one A here. Since that A being in S will now belong to the union, so it must be in at least one of the sets. We have A belonging to A for at least one or for some set in the partition. But then A and A belong to A. It seems like there is no point in writing this because here we are just mentioning something twice. A belongs to A as well as A belongs to A, but because of the way we have defined the relation, this is necessary. But then this, which implies that A is related to A. And since we chose small a to be any element in S, this is true for every element in S, and that's why the relation is reflexive. Hence, this is reflexive. Ideally, you should mention this. After writing this line, you should mention that since B chose small a in S to be an arbitrary element, so every element is related to itself, and that's why the relation is reflexive. But usually such details are not shown. There is no hard and fast rule how much you should show and how much you should not show in a solution or a proof. The more you deal with these things, you will understand how much you should write and how much you have to suppress. Because gradually many things will be obvious. So it makes sense to suppress them. Although that is not ideally how things should be written, but we do that for the sake of time and space. Okay, so now this relation is reflexive. Next, symmetry. Next, let A and B be two elements in S such that A is related to B. Then we apply the definition of our relation. Then there exists some set A in the partition such that A is in capital A and B is also in capital A. But this implies that B is in capital A and A is also in capital A, which is just the same thing said in a different manner. Hence, B is also related to A. Thus, tilt is symmetric. Reflexivity and symmetry have been, as you can see, almost trivial. Transitivity, however, is not like that. Next, let A, B and C be three elements in S such that A is related to B and B is related to C. Then there exists now, because we have two relations means two pairs of related elements, so we will have two sets which may or may not be the same, we don't know as yet. Such that A and B belong to A and B and C belong to B. Okay, now note that the element B belongs to both capital A and capital B. Since small b belongs to, and because of that it belongs to their intersection, and the sets belong to P, and P is a partition. We must have A equal to B. That is because the sets being elements in a partition are either distinct or disjoint. Now they are not disjoint because small b is there in both of them. So that means they cannot be distinct. So they have to be equal. But then, because they are equal, A and C both belong to A. C originally belongs to B, but B now we have shown is nothing but A. Hence, since A and C belong to the same set in the partition, so A is related to C. So the relation tilde is transitive. We have thus proved that our relation is an equivalence relation. I need ink. Give me a moment. Fine, but that is only half the job. Now we have to show that the equivalence classes of this relation are actually nothing but the sets in P. Okay, for that, in fact, let's just write that first. Now we show that the set of all equivalence classes of our relation is nothing but P. So that means we need to concentrate on some equivalence class. So let's start. Let A be any element in S, so that we can consider the equivalence class containing A. There exists a set A in the partition such that our element belongs to that set. In fact, because we are talking about partitions, this capital A will be unique. It's like this. Now, this is our S, and here we have the sets in the partition. The sets are mutually disjoint. There is no non-empty intersection between two distinct sets. The sets themselves are non-empty and their union is the entire S. So this A being in S is here somewhere, and the set in the partition that has A, that is unique, capital A. This A cannot be anywhere else, I mean in no other set in the partition, because the sets in the partition are mutually disjoint. Okay. Now we want to show that the equivalence class of A is actually equal to capital A. For that, we proceed like this. By the definition of the relation, tilde, we see that A is related to B for all B belonging to capital A, because that's how we have defined our relation tilde, right? The relation says that two elements in S are related when they belong to the same set in the partition. So all the besides A, there may be some other elements in capital A. Because those elements belong to the same set capital A as small a, so all of them individually will be related to A by the definition of our relation. This implies that B belongs to the equivalence class of A. The equivalence class of A by definition is the set of all elements in S that are related to A. So B being related to A means B is coming from the equivalence class of A. So this line implies that for all elements in capital A, they belong to the equivalence class of A. For all B belonging to A, that is, A is a subset of the equivalence class of A. You take any B from here that is related to small a, and as such that belongs to the equivalence class of A. Okay. Now what about the reverse inclusion? We should now show that this is also a subset of this. For that, conversely, let C belong to the equivalence class of A. Then C is related to A. C is related to A or A is related to C. If you write any one of these two, it does not matter, because the relation is equivalence, so it is symmetric. So if one of them is true, the other is also true. Then C is related to A, and hence there exists some set in the partition such that A and C both belong to that set. Okay. Since we already have our element A belonging to capital A, that is already there because that's how things started, and these sets A and B are after all in our partition, so A and B must be identical, they must be the same. If they are distinct, then because they are in the partition they should be disjoint. However, this common element A prevents them from being disjoint, so they cannot be distinct, they have to be identical. We must have A equal to B, but then C originally belongs to B, so now C belongs to A. So C is any element in the class of A, C must belong to A. So the class of A is also a subset of A. Now you combine these two inclusions. We thus have okay, so what have we shown here? We have shown that every equivalence class, because choosing an arbitrary element A in S means choosing some equivalence class, namely the equivalence class containing that element. We have shown that any such equivalence class is a set in the partition. It is a member of the partition. Now we have to prove the converse, that any set in the partition is after all an equivalence class. That way we will see that the sets in the partition are actually all the equivalence classes. Next, so this time we are going to consider any arbitrary set from the partition. Let us take capital C belonging to the partition. Since now note the fact that because C is a set in the partition, that means C first of all is a subset of S, and that too is a non-empty subset of S. Since C is non-empty, there exists some element, say small c, or you can take D also to avoid confusing with this C here, for example, D in C. Okay, now we want to claim that the equivalence class of D is actually equal to this set C. If we show that, that will prove that this arbitrary set in the partition is an equivalence class. Okay, so for that we have to proceed just like this. The only difference is that instead of now starting with an equivalence class and an element in that class, we have now started with a set in the partition and an element in that set. Okay. So without thinking much about the situation, let's just get down to showing that this is equal to the class of D. So let us choose any element E belonging to C. Since D and E both belong to the same set C in the partition, so according to the definition of our relation, E and D will be related. And hence E actually belongs to the equivalence class of D. So any element in C belongs to the equivalence class of D. So C is a subset of this. Conversely, let F be an element in the equivalence class of D. Then F is related to D and so there exists some set D in the partition such that F and D both belong to capital D. Since we already have D belonging to C, because this is where this part has started, and capital C and capital D are sets in the partition, so not being disjoint means they have to be identical. We must have D equal to C. But then F belongs to C. F is in D, so now because of this equality, F belongs to C. So F was chosen to be any element here in this class. We have now shown that F belongs to C, which implies that this is contained in C. So like before, we now combine these two inclusions. We thus have So besides showing that every equivalence class is a set in the partition, we have shown that all the sets in the partition are also equivalence classes. So the set of all equivalence classes of our relation is P. That's just what we had to show. So now the solution ends. Now, based on the solution, and based on this solution, we can answer the next question, next exercise. Find an equivalence relation on the set of natural numbers having exactly two equivalence classes. One of which contains exactly 3 elements. So some equivalence relation we have to define, corresponding to which there are only 2 equivalence classes and one of those classes has exactly 3 elements. So because of the one-to-one correspondence between equivalence relations and partitions of a set that we have seen in this previous exercise, we can easily use this idea to define such a relation. For any two natural numbers we define A to be related to B if either A and B both belong to the set consisting of these 3 natural numbers 1, 2 and 3, or A and B both belong to the complement of this set. So you can see that the general equivalence relation we defined here in this solution, which corresponded to a given partition of the set S, now that reduces to this particular partition of the set N, where we have only 2 sets. One set in the partition is this and the other set is its complement. You can clearly see that these 2 sets form a partition of N. Why? Both the sets are non-empty, they are disjoint and their union is N. So here the definition of this relation is nothing but that itself. In this particular case, the definition reduces to this. If you don't want to use sets in the definition explicitly like this, showing that they correspond to this partition, you can also define like this. Same thing, if either both A and B are less than or equal to 3, or both A and B are greater than 3, corresponding to these 2 containments. If both of them are less than or equal to 3, then they belong to this set, otherwise both of them belong to that set. clearly this is an equivalence relation with the two equivalence classes. Oh, in this book we are not using this notation. No? For set difference we are using this. So we have precisely two equivalence classes and one of them has exactly 3 elements. That's just it. Suppose there is a relation rho on a set S. Such that rho is both reflexive and transitive. Define another relation tilt on S via this rule: A is related to B if and only if you keep saying in some definitions just if, and whereas in some places in definitions you see if and only if, just know that they mean the same thing, although they actually don't mean the same thing. If when you write something like this, say a statement P if Q, that means one thing, and if you write P if and only if Q, which as you may know in short we write if and only if as IFF. Really these two things mean these two statements. This one means that Q implies P, whereas this one means that Q implies and is implied by P. Logically they are different. However, because you are defining something, once you mean that this means this, that's the only meaning it has. You are defining. So in definitions, if and only if mean the same thing. You can use any one of them. Sometimes we use if and only if to reinforce the fact that tilt means this and this means tilt. Okay, anyway, if and only if A is related to B by rho, by our original relation, and at the same time B is related to A by rho also. Show that tilt is an equivalence relation. Okay, instead of considering elements again and again, let us in the beginning itself take three elements which may or may not be equal. I mean, not necessarily distinct. When we say in mathematics we take three objects, the possibilities that some of them are the same object is there. Okay, we don't mean distinctness always. So let A, B and C be three elements in S. Since rho is reflexive, that is given, we have A related to A by rho, and A is related to A. The way we have defined tilt demands that we have these two things, which in this case become the same thing. So now A is also related to A by tilt. Thus this is like rho reflexive. Next, let A be related to B. Then A is related to B by rho, or sometimes this is also expressed by saying A is rho related to B and B is rho related to A. That is saying the same thing in a slightly different manner. B is rho related to A and A is rho related to B. Hence, B is related to A by tilt. Thus, this is symmetric. Finally, let A be related to B and B be related to C. Then A rho B and B rho A and B rho C and C rho B. Since rho is transitive, the relation with which we started, rho, that is given to be reflexive and transitive. Symmetric, rho is symmetric or not, that is not given, and we don't need that anyway. So because rho is transitive, A rho B, and we have A rho B here and we have B rho C. These two things imply that A is rho related to C. Like that, B rho A and C rho B. Actually we have to write this one first to show transitivity properly. C rho B and B rho A imply that C is row related to A. That is A row C and C row A. So A is related to C. The relation tilt is thus transitive. Hence, this is an equivalence relation. If you think of relations means if you really go to the definition of a relation, the original set given was S, right? So the relation row on S, that by definition is a subset of S process of this Cartesian product. Reflexivity of row means all these ordered pairs belong to row for all A belonging to S. Transitivity, of course, means you know what. So to make this relation symmetric, this relation, of course, you cannot just simply do something to the relation, make it symmetric and keep the relation intact. You have to introduce new ordered pairs. If originally row had this ordered pair A comma B and now it does not have, you need to introduce the what the hell did I just say? If A comma B is in row but B comma A is not in row, now in your new relation you need this to make it symmetric. That's what we have done when we defined tilt. So the next few exercises are about functions. Define alpha from this set to this set of the first 7 natural numbers. Via this formula, alpha of A is defined to be equal to 2A minus 1. Is this function 1 to 1? And is this function onto? The names of these properties, one-to-oneness, onto-ness, the names are very good names. The names almost tell you entirely what these properties are. One-to-oneness means like this. This is your first set, this is your second set. One-to-oneness means 1 to 1 as opposed to 2 to 1 or many to 1. Okay, so that means for 1 to 1 functions, distinct inputs should give you distinct outputs. Here in a many to one function, you may have distinct inputs but may end up with the same output. In one-to-oneness, all the arrows are parallel, if you want to say express this situation by saying something like that. Like that, onto-ness means the entire shadow of the domain, it covers the space, covers the second set, this space completely. This is an onto function because the set of images is this, which is equal to the second set, which sometimes also we call codomain. However, this function is not onto because this single element has been left out. Here, the shadow of the domain is only this much. You can of course understand that these are sets and these dots represent elements. Okay, so now what about this function? Because there are only a few elements in the domain and also only a few elements in the codomain, so you can calculate the images. 1, 2, 3, 4. So the image of 1 is 1. The image of 2 is 2 times 2. 4 minus 1 is 3. The image of 3 is 5. And the image of 4 is 7. So you can see that this is actually one-to-one, although we have not drawn the thing somewhat like this so that the arrows are parallel, but you get the point. Different inputs have different output. From a single point here, we don't see two arrows attacking that point. There is only one attack. So that's why this is one-to-one, but clearly it's not onto because there are left out elements which have not been attacked. These are just for the sake of understanding, of course. We will now have to write the rigorous solution. Note that alpha of 1 is 1, alpha of 2 is 3, this is 5, and 4 is 7. Since distinct inputs have distinct or you can, instead of calling them inputs, distinct elements, then we have to additionally write in the domain have distinct images. Alpha is 1-to-1. Whereas alpha is not onto because there exists no A belonging to the domain such that alpha of A is say 4. For lack of ontoness, you just need one counterexample. 4 has no pre-image or inverse image, so alpha fails to be onto. Next, okay, this time the sets involved are infinite. So both the domain and codomain are the set of real numbers, and the formula for the function is this: cube root of a plus 1 minus 2 is this function one to one, is it onto? When you get a function defined like this, you should always see whether the function is well defined or not, that is, whether there is no problem with the formula for the function. Had this been square root, we would have had a problem, because you cannot have negative real number inside square root. You can have, but that will give you complex numbers that are not real. Here, however, because you have cube root, there is no problem. Any nth root where that n is an odd natural number will give you no problem. If it is even, then you will have a problem. Then you will have to restrict the domain in order to keep the function real valued, that is, in order to have real outputs. Had this been 2, we would have required a plus 1 to be non-negative. A plus 1 in that case cannot be negative. So the domain in that case would have been restricted to this interval. On this interval, if you choose a from here, then a is greater than or equal to minus 1, so a plus 1 will be non-negative. Anyway, so let us now see whether this function is one to one or onto, and or onto. Now the set we have is infinite, so we cannot possibly draw a figure like this. We can, however, analyze analytically. For A1 and A2 belonging to R, let alpha A1 be equal to alpha A2. You can do one of these two things to show that a function is one to one. You either take two different inputs and show that their outputs are different. That is, if you take, for example, like here we have taken A1 and A2 in the domain. Assume that they are different. Then prove that, say your function is f. Prove that the outputs are also different. or you can prove the contrapositive of this statement, which is also logically equivalent to the statement B. This is an implication. The contrapositive is what? This is, say, your statement P, this is the statement Q. P implies Q means negation of Q implies negation of P. That is, negation of Q is f of A1 equal to f of A2, implies negation of P means A1 equal to A2. That is, instead of showing that distinct inputs give you distinct outputs, you can show that for two chosen inputs in the domain, of course, if the outputs are the same, then the inputs must also be the same, because otherwise it will be a many to one function. So if this is true, then this is true. So that's what we are now going to do. That's what we have assumed. Then let me keep this, okay. Cube root of A1 plus 1 minus 2 is equal to cube root of A2 plus 1 minus 2, which implies after adding 2 on both sides, and then taking cubes, so we see that indeed this is true. Hence, alpha is 1 to 1. Okay, now what about ontoness? For ontoness, you take any element in the second set in the codomain, which for us is again R. Show that R is the output for some input. That some input we have to find. Now so what can we take? Let us take B, because why we do this? Because we want to show that everything is being attacked. Nothing is safely sitting here alone, which is not coming in contact with anything from the domain. We want to show that such lonely elements are not there in the codomain. Then that will give you an onto function. So let B be any element in the codomain. Now what we want is some A such that this is true. So to find A, solve for A, while doing this type of calculations, always keep in mind, no matter how casual the calculation looks, no matter how familiar you are with this type of calculations, it's better to take things seriously so that you don't make mistakes. Here, adding 2 on both sides give you this. Taking cube root on both sides gives you this. You have to know that what you are doing is actually it's justified logically. Sometimes it is not, and those are the times we make silly mistakes. So that means this is our something from which B will come. that is b plus 2 whole cube minus 1. And clearly for any given real number b, this is also a real number, you also have to make sure that the something you have found as your pre-image, that should belong to the domain. Here the domain is very large, it has all the real numbers, so there is no problem, but sometimes there are problems. So b plus 2 whole cube minus 1, but this we don't need now. Then this is also a real number, this will be equal to b. You can do the calculation. We have seen how this pre-image or inverse image has come. Hence alpha is onto. I am again repeating something that I have repeated many times by now. In any of these solutions, there may be some mistake which I may have overlooked in the haste to write the solution or in a frenzy to write solution. We all make mistakes. So if you spot any mistake somewhere or any inconsistency or any confusion, please let me know in the comment section below. Okay, otherwise some wrong solution may remain forever. So alpha is both 1 to 1 and onto. Okay, so here the solution ends. Next, exercise 25. Let S be the set of real numbers and T be the set of positive real numbers. S be the set of all real numbers. Define a function alpha from S to T via this formula. Alpha of A is equal to 2 to the power 3A minus 5. Show that alpha is the bijection. That means alpha is both 1 to 1 and onto. Show that alpha is the bijection and find a function beta from T into S such that beta alpha A is equal to A for all A belonging to S. That means not only do we have to show that the function alpha is a bijection, it's both 1 to 1 and onto, we have to find the inverse of the function alpha. Only when a function is bijection does its traditional inverse exists, and that inverse is beta. And by definition, inverse, and if you compose the function and the inverse in a proper way, the elements on which you can apply that composition will not be affected, because now this becomes the identity function on S. If you change the order, if you write alpha first and then beta, that will also be an identity function, but on T. Okay, so the first half is just like before. We need to show that alpha is 1 to 1 and on 2. So we start by showing it's 1 to 1. Let A1 and A2 belong to S. Such that alpha A1 is equal to alpha A2. Then alpha A1 means 2 to the power 3A1 minus 5, and alpha of A2 means 2 to the power 3A2 minus 5. Okay, this means minus 3A2 minus 5 equal to 1. So here we have divided both sides of this equation by this right hand side, and we can do that because such a power is always a positive real number. A power like this never becomes a negative real number, and it's also never zero. Positivity or negativity, that does not matter here because we have equality, but non-zeroness matters. If it is 0, you cannot divide by it. And then after that division, we have used one of the rules of exponents, this one, 2 to the power k divided by 2 to the power L is equal to 2 to the power k minus L, that thing. Okay, so now this becomes 3A1 minus 3A2 is equal to 1. Now if you look at the function 2 to the power something, that something can be any real number. If you draw its graph, the graph crosses the x-axis at exactly no, that's not what I want to say. The graph crosses the point 1 on the y-axis precisely when the exponent in this power is 0. In no other situations the graph will look like this. Roughly the shape of the graph will look like this. As your exponent decreases, it becomes, the moment the exponent becomes negative, if your x is here, then 2 to the power x, the value will be smaller than 1. Then it will continue getting smaller and smaller, never becoming 0, but that process of gradual decrease, that will continue. If your value input is greater than 0, if it's a positive real number, then this will be greater than 1. Only at x equal to 0 do you have 1. So that means this implies equal to 0. The exponent should be 0. If however your this a1, a2, these are allowed to be any complex number, then it will be a different story. And this implies cancelling 3 from both sides, a1 equal to a2. So outputs are equal implies inputs are also equal. Hence alpha is 1 to 1. Next, let B belong to T. Keep in mind that now we are not having any real number B. We have a positive real number B, because according to the exercise, T is the set of all positive real numbers. So like before, we want to find an inverse image for B under the function alpha. So if that inverse image is A, we want this. That means we want this. Solve this for A. Take logarithm on both sides to the base 2. You get 3a minus 5 is equal to log b to the base 2. So 3a is equal to plus 5 and a is a third of this. So that means this is our inverse image. Then this belongs to S such that the image of this real number is equal to B. Note that we have been able to write log B because B is a positive real number. For negative real numbers, also their logarithms exist, but they are complex, non-real complex numbers. For 0, however, it does not exist. Anyway, we don't have to think about such cases. For us, B is positive, so everything is fine. Thus, alpha is onto. Also, if we define the function beta from T into S, this formula beta A equal to here also we are writing A. Here also we are writing A. That may create some confusion. Let's keep B. Belonging to S. So this is our inverse function. Note that because your original function is an exponential function, although it's not just simply 2 to the power a 2 to the power another function of a, and that function is 3a minus 5, but after all an exponential function. So the inverse function involves logarithm. In the exponential function the base is 2, so in the inverse function the logarithm that you find also has base 2. Okay, now next we come to a piecewise defined or partly defined function which uses different formulas in different parts of its domain. These type of functions often confuse us if we have doubts about what they really mean. Define alpha from R into R via this formula. Alpha of A is defined to be 4a minus 3 when A is less than or equal to 1 and is defined to be a square when a is greater than 1. Do not be intimidated by these multiple formulas. It just simply tells us that here we have 1 somewhere on the real line. On this part of the domain, the entire domain is R. On this part of the domain, including the point 1, the function is 4a minus 3. And on this part of the domain, for input values greater than 1, the function is a square. That's just it. Okay, but now what do we have to do? Again, I believe the same thing, one-to-oneness, onto-ness. Show that this alpha, okay, this alpha is also bijective. Alpha is bijective and find by now you can see that finding the inverse function really comes from the calculation that shows you that a given element in the codomain has this inverse image. From the formula for that inverse image, you easily get the inverse function. Yeah, find beta again from R to R such that the composition beta alpha behaves like the identity function on R. Okay, now in this solution, after this stage, there is we don't have a single calculation like that what we have been getting so far. It's because there are in different parts of the domain of alpha the formulas are different, so some cases will arise. If a1 and a2 are both less than or equal to 1. That is, if both of them belong to this half open, I should not say open, anyway, belong to this interval, then that means we have to use this part of the formula. 4a1 minus 3 is equal to 4a2 minus 3, which implies a1 is equal to a2. On the other hand, if a1 and a2 are both greater than 1, then we have to use the square part of the formula. Which implies a1 is equal to a2. But how are we able to write a1 equal to a2 so fast without thinking of anything else? You see, because a1 and a2 belong to this interval, both of them are positive. So we will not have a1 equal to minus a2. That possibility will not appear. And that's why we are having this. In fact, within brackets you can write, note that a1 comma a2 are both positive. Fine. So in both these cases, the inputs turn out to be equal, but they are not all the cases. There is a third one. Actually, there are two more, but without losing generality, you can assume one of them. Namely, that a1 is less than or equal to 1, but a2 is greater than 1. If a1 is less than or equal to 1 and a2 is greater than 1, then what happens to these expressions? Because a1 is less than or equal to 1, 4a1 will be less than or equal to 4. Subtracting 3, you get 4a1 minus 3 less than or equal to 1. Do you see this? You add 3 on both sides, you get 4a1 less than or equal to 4. That gives you this, and conversely, from this you get this. Whereas, because a2 is greater than 1, so a2 square is also greater than 1. So in this case, this is what? This is alpha a1 strictly less than alpha a2, which contradicts our hypothesis. I mean, we have chosen a1 and a2 in such a way that these images must be equal. So that means this case actually cannot occur if we are insisting that we have this. So we cannot have a1 less than or equal to 1 and 1 less than a2. Similarly, we cannot have a2 less than or equal to 1 and 1 less than a1. So now all the cases have been explored, and in the remaining cases, I mean not these two but the others, we have seen that we get that the inputs are also equal. Thus alpha is 1 to 1. Now ontoness. Next, let B belong to R. Just like one-to-oneness, for ontoness also we have to look at the two different possibilities. If B is less than or equal to 1, then B plus 3 divided by 4 is also less than or equal to 1. How are we getting this? Add 3 on both sides. You get B plus 3 less than or equal to 4, then divide throughout by 4. That gives you this. Such that alpha of B plus 3 divided by 4 equal to B. Because of this inequality, this will be 4 times B plus 3 divided by 4 minus 3. On the other hand, if B is greater than 1, then the square root of B is also greater than 1, such that this is equal to B. Hence, alpha is onto also if we define beta from R into R via this formula, beta of B equal to, like before, the formula for beta will now come from these calculations. B plus 3 divided by 4 if B is less than or equal to 1, and square root of B if B is greater than 1. Then beta alpha of A is equal to A for all A belonging to R. Just one more thing, note that here there is no problem in taking the square root of B because B is positive, so its square root exists, which is a fact you know from real analysis. Next, which of the following are binary operations. Some more ink. Oh, binary operations on what? On n, on the set of natural numbers. S star B is AB. And the second one, S star B is A minus B. And the third one, S star B is 3 for all A and B. So a binary operation on a set S is nothing but a function with domain X cross S and codomain S. So in these formulas for the function, for the corresponding function, you just have to see whether that thing is true. And in the notation that we usually use in writing a binary operation, say your function f is this, then the function f itself is called a binary operation on S. But instead of writing the image of this input a comma b, which belongs to the domain, as f of a comma b, we write AFB. And also, in place of some letter f, when we have an operation, we use some symbol like plus. This is a function on n. Function on n means a binary operation on n, which is a function like this. Instead of writing this function really gives you the output 5 when the input is the ordered pair 2, 3. Instead of writing like this, we write like this, that is 2 plus 3 equal to 5, because this looks less cumbersome than writing plus of 2, 3. The fact that plus of 3, 2 is also 5 is your usual commutativity, that the binary operation is commutative. Okay, so now here we have to see whether these given functions are binary operations. So the first one is product of two natural numbers. We know that when we take the product of two natural numbers, that is again a natural number. Since the product of two natural, or in fact, in order to emphasize that we are after all talking about functions, let's write like this: since the product of two given natural numbers is a unique natural number, is a binary operation. We call such operations binary because there are two elements involved in the input. If you have n elements involved, you will call it an n-array operation. Number two, this is not a binary operation. Star is not a binary operation because for 1 and 2 belonging to n, 1 star 2, which is 1 minus 2, is not in n. So this star does not represent a function from n cross n into n. So that's why it's not a binary operation. The third one is again a binary operation, although it's a very uninteresting and dull operation. Its only output is just 3. Nevertheless, it satisfies the conditions in the definition, so it is a binary operation. Since for given a and b belonging to n, a star b, first of all, for given a and b belonging to n means given ordered pair a comma b belonging to the Cartesian product of n with itself. For that input, you have an output in n, and that output is unique. So that's why this is a legitimate function, and as such, the corresponding star is a binary operation. Let S be a finite set. And suppose that alpha from S into S is a one-to-one function. Show that alpha is a permutation on S. Permutation is a bijection from a set onto itself. So that means here we have to show that alpha is a bijection. and that requires us to show that alpha is onto. It's given to be 1 to 1, so we just need ontoness extra. Construct an explicit example. Example means counterexample. If you want to show that something is not in general true, and in that process you the way you show that is by presenting some particular example, that is called a counterexample to that thing which you want to show is not in general true. Counterexample to show that this need not be true if your set is infinite. The finiteness is necessary here, because we are not treating finite sets in this book with, what can I say, with the level of rigor that you see, we can precisely define finite sets. There is a definition. We are not using that definition here. That definition involves again bijections, like what the functions we see here, and identifying finite sets with some particular types of finite sets, namely this type of sets. Then defining cardinality of a set. That's how one should proceed and define finite sets, then prove many properties of finite sets with which we are already familiar. But that's not the route we are taking here. Here, by a finite set, we just vaguely what we know as finite set, they are considered to be finite. So in that vague manner only finiteness is being treated in this book. So the solution will also be like that. So we are given a one-to-one function alpha on a set S. We want to prove that it's onto. Since alpha is 1-to-1, the image alpha of S has the same number of elements as the domain S. You can imagine why that is true. You again go to those little figures that we can draw of functions. If this is your S, we have S only, of course. Now if we had a different set, say, just to give you an idea of what we are not seeing here, if you had a different set T and your alpha was not 1-to-1, then you can see that, so this is a general situation where there are two arbitrary sets involved. Both of them are finite, however. Here the function alpha is not 1-to-1. because of these two elements having the same image under alpha. And you can see that because of this not one-to-oneness, the size of the image set alpha of S has decreased. S has 3 elements, whereas this one has 2 elements. But because alpha is one-to-one here, so that collapse or shrinkage is not available in this case. So alpha of S will have as many elements as S has, and this number of elements, we can talk about number of elements because the sets we are dealing with here are finite. But the image is a subset of S. So this is a subset of S which has the same number of elements as S. So then they have to be equal. Hence, alpha of S must be equal to S. And so alpha is onto. Being one-to-one and onto, alpha is a permutation on S. Now next we have to provide a concrete counterexample to this fact. If S is infinite, then this no longer is true. A one-to-one function is not necessarily onto, and as such is not necessarily a permutation. Consider the function alpha from the set of natural numbers into the set of natural numbers. So in place of S now we have the set of natural numbers, and which is infinite, where alpha of n is equal to n plus 1. Okay. Clearly alpha is one-to-one, which you can almost immediately see. You take two distinct natural numbers, their next natural numbers, which you obtain by adding 1 to them, they are also distinct. So different inputs have different outputs. So this function is one-to-one. But alpha is not onto because we have no n belonging to n for which alpha of n is equal to 1. So the element 1 does not appear as the output for some input. There is no input that gives you 1, and this function looks like this. If you draw the diagram, the image of 1 is 2, that of 2 is 3, and so on, like this it will go. So the one-to-oneness is there, but onto-ness is not there. So if your set is infinite, then this property may fail. It's not that it will always fail. If in place of this function you took your ordinary identity function, that is of course both one-to-one and onto, but the property is not necessarily true if finiteness is dropped. So the solution ends here. This figure is extra. Let alpha from R into S and beta from S into T be functions. And suppose that beta composition alpha is onto. Must alpha also be onto? Must beta be onto? Okay, so here we have two functions. This is your alpha, this is your beta, and we have the composition beta alpha. This is given to be onto. So the shadow of R under beta alpha is all of T. Is that also the case with alpha, and is that also the case with beta? We have to answer that. This we will solve along with other exercises in the next video, which will be there next Saturday. Okay, now some things about. So today's video ends here. Now, why did I not upload a video yesterday? It's because, you see, there are two things. First of all, do you remember that I said that if our Gregory Lee's algebra exercises, this type of videos clash with the usual schedule, then I would tell you about these uploads in advance, that is at some other time. However, I did not do that. I forgot to do that. So I planned to upload a field theory video yesterday, and I planned to upload this video tonight, which I am doing. However, the field theory video was not, I was not able to film it because of a peculiar problem. Although you may not be interested in it, but I would like to say some things here about what we were doing in field theory from Herstein's topics in algebra. We are at the stage where it seems like we have proved that the number E is transcendental. We have gone through the proof that is given in the text, and I said in the video, in the last field theory video, that there are some issues in the proof which we will address in the next video. So I was going through those issues. You can easily make sense of all the things, and whatever little details we did not provide back then when we had that field theory video, we can easily provide those details now. But there is one problem. At one stage I noticed that we used some inequality which estimates the size of epsilon s. Something is there, but the arguments used in the proof don't make it clear that these inequalities are true. I mean, most of the things are true, but I am finding it difficult to believe that the epsilon i's, we gave some upper bound for this absolute values of the epsilon i's. there is a problem with one part in that upper bound. And I think that problem is actually a mistake. If it is really a mistake, then we should rectify the proof. Or the best case scenario is that I am missing something obvious, so I will upload a video tomorrow about that problem itself, and we will see where things go. Okay, so today is what? Today is 6th, but I was supposed to upload on 5th, so that means 5th, 6th, 7th. So on 8th of this month, we will have the next upload, and the next upload will be what? Group theory, field theory, then vector spaces and modules. From topics in algebra by Herstein. And tomorrow I will upload that field theory video where we will address that problem. If it is really a mistake in the proof, then we have to rectify it. Rectify means we have to change the proof slightly. Or if I am missing something, then of course we will see, okay, what ultimately things turn out to be. So that will be all for tonight. If you want to comment on these things, you can write in the comment section below, or you can mail me also at this address. Let me again write it. So with that, I end this video. See you in the next video. This is me, Lucifer, from a mathematical room. Have a nice night.